All right. I don't typically put my certs on my slides, but in this case, I want to put OSCP up there for a particular reason. And that reason basically is that when you go to events like this, I think it's really important to seek beyond what you typically go to. As an OSCP, I mean, I love popping boxes. I love red teaming. You know, it's super exciting. But then I went to this talk at BSides Los Angeles and kind of got a feel for this book. And it's all about what we're going to talk about today. And it was interesting to me. You know, okay, so if popping boxes is like up here, quantitative risk is, okay, it's not there, right? It's not popping boxes. And this microphone is really going to kill me, isn't it? It's not popping boxes. You know, I don't do a jubilation dance when I quantify a risk, but it is very interesting to me. So I just want to encourage everyone to reach beyond their normal knowledge when they go to these conferences. Don't go to the same things all the time. And that's basically that. So this is the book. It's all about Monte Carlo and quantitative risk analysis. Has anyone here read this book besides me? I got a few, all right. Does anyone here know anything about Monte Carlo analysis? The same people that read the book and a few more. Okay. I just want to judge how much of the basics I should go through, and I'm going to go through them pretty close then. Okay, so we're going to go through that. Then I'm going to go through what I learned as I started applying this at my actual job, what I work at right now, and kind of the issues I ran across. And so Hubbard's book is great. It's fantastic. It comes with a free set of tools you can download. It's got Excel spreadsheets you can work on. I found I couldn't ask questions of that spreadsheet fast enough, so I wrote the whole thing in Python, and that's all available online on my repo, which will be at the end of the talk. You'll see it. So you'll see all my tools are available, including the risk decomposition spreadsheet you're going to see, and my sample risk that I'm going to show you, the whole model that I used. So if you need to get into this stuff, the book is a great place to start, and you need to start there. And then use his tools, and then I think you'll want to move on to another set of tools very quickly. And I'll talk about my application of what I really did at my current job, and my results of my first risk I modeled like just 2 weeks ago. And then I'll go into what I'm doing next. Okay, so the idea. We all know what risks are. Risks are an event that has a possibility of happening, and it has an outcome we don't want, right? On a qualitative risk analysis, we use this heat map, right? We go, hey, we're gonna subjectively, qualitatively assess the risk as far as how often it's going to happen and how high the impact is, and we plot it on a chart. Quantitative risk is the same. It's a subjective assessment of the risk, both the probability and the impact, and you model that and you plot it on a chart. There's really no mental difference between how you do it. I'm not going to go through this chart you're seeing right here in detail, but it's the same thing. The biggest complaint I hear when I start talking to people about quantitative risk is the numbers aren't there, it needs to be exact, it has to be based on data, we don't know the data for breaches. None of those things are true when it comes to modeling risk with Monte Carlo and quantitative risk analysis. It is subjective, and the difference is instead of just picking a number or a category like high or very low, we stake a claim, we assess the risk based on a measurable, observable scale. And we're going to go over how you do that. And it's absolutely possible and absolutely can be done. And the best part is that when the data changes, you can remodel very quickly. And you can easily compare your risks because they're on the same scale. So if you get risks from source A and you get risks from source B, this has happened to me, I'm sure it's happened to all you guys, if they're on the same basis, you can combine them. When they're on two separate heat maps with these linguistic terms, you can't combine them. You really don't know. You don't know how many of those risks in the green add up to a risk in the yellow. There's no way to know that. But with the quantitative risk done properly and on a proper scale, you can. And that's why I really like quantitative risk stuff. As an engineer, it super appeals to me. Okay, a quantitative risk. First, you start with the probability of occurrence. Instead of saying it's likely or only a little likely or never going to happen, you have to pick a number. You have to assign a probability. And this is tricky and difficult. And we're going to talk about the impact it has on your models later. But you do have to pick it. And you can express a range for uncertainty. You can say there's a 12% chance, or there's a 9 to 14% chance, or any other kind of distribution for probability you want to use. You can use it. All right. And then the loss. Hubbard talks about loss almost solely in the terms of log normal. This is a standard distribution for real-life activities and processes that exist in the world. And I'll show you a graph of that in a second. And basically, you have to pick two numbers, the lower bound and the upper bound. The upper bound is you're saying, hey, 95% of all events will have this impact or less. And I'm going to show an example of this in a second. And then the lower bound, you pick, hey, 95% of all occurrences of this event have this impact or more. You pick those two numbers, you use the log normal distribution, and you get a very close to real life distribution of what kind of impacts you can expect. And the interesting thing about log normal is this great tail out here. Oh, look, I can use my finger. This great tail out here shows low probability but high impact events, and we call those your black swans, right? Log normal captures that for you, and it's super useful. Now, do log normals exist in real life? This is a graph from Blackline. Blackline is a financial services company that exists in the valley where I live. I don't work for them, but this is on their website. And this is it's saying average days for assignment completion, and you can see it matches the log normal distribution. Most of them are clustered around this 4-day mark. You've got some that happen very quickly, and you have other ones like when your paycheck gets released, happen 20 days later, right? So so it kind of shows the black swan effect, and it shows the log normal. So that's just to kind of show you that log normal is a real thing, and there's lots of like real life processes that mimic this distribution, and that's why we use it for our quantitative risk assessment. Okay, picking the numbers. How do you pick your numbers for that lower end and upper bound for things you don't understand and don't really know? Like the impact of a breach, right? Very difficult to pick those numbers. One thing I didn't cover real quick is I'm going to do all of my breach effects in cost. I use almost nothing but dollars because that's what businesses work on. However, in a previous life, I worked for a defense contractor, and I was working on the an Air Force weapons system, and I attempted to start tying cyber breaches to the root mean squared error that weapon system may expect with a cyber breach. The point was it's a measurable, observable effect that you can estimate based off of however you want to estimate it, and you can use it. So it doesn't need to be dollars. If you work in a world that doesn't require dollars, then you don't need to, but it needs to be measurable, observable, and a proper ratio scale, a real number scale. You can't just have a made-up number scale for you to make it work. Okay, so back to this. So how do you estimate your numbers? So Hubbard goes into this in detail, and it's called calibration of the experts. And it turns out there's plenty of research that shows you can take a person, you can expose them to things they don't know anything about, lots of things they don't know anything about. You can learn how to estimate the lower bounds and upper bounds in a way that you are right 90% of the time, that the real answer is in between. It's called calibration. His website has 4 calibration tests you can take. I've taken one, and I came out 70% confident, which means I'm actually overconfident, which means the numbers that was right was out of the bounds I picked too many times. All right, you want to be 90% confident, which means I need bigger ranges, bigger lower and upper bounds. So and it works like this: you get a question on something you have no experience with. What is the stated capacity of Wembley Stadium in London? And you start thinking about it. Okay, we can go absurd. We can go, the lower bound is at least 1, right? At least 1 person can fit in Wembley Stadium, right? The upper bound, 1 million. There's no way more than 1 million people fit in Wembley Stadium and live, right? Okay, so we have this giant range. But now we got to think about bringing that range together because that's too much uncertainty, right? It's not useful information. So then you say, okay, I don't know, 10,000. The minimum is 10,000. At least 10,000 people fit in Wembley Stadium. And maybe the upper bound's 500,000. Okay, and you start getting to a smaller range, and you hope that the answer is right in there somewhere. And the point is, you do what he calls an equivalent bet. All right, it doesn't even matter if it's real money or not. You say, okay, for 1,000 imperial credits, would you rather spin that dial and land on the green, or see if your answer is right? That your range includes the actual value. And the point is, you keep reducing the size of your range until you don't know if you want to spin the dial or you want to find out if you were right. So, we can play with that. We can say, okay, we said 10,000 is the lowest and 500,000 the highest. I know that the answer is in there, right? I don't think any stadiums seat 500,000 people. All right, so I can bring it in. 50,000 to 250. What do I want to do? What do you guys do? Do you want to spin the dial? Or do you want to see if your answer is right? What's the crowd? What do you guys think? Crowd's dead. Nobody cares. What's that? 200,000. Okay, so he's playing the game with me. He's saying, okay, we'll get to 200,000 and we're at 50,000. Now, do we think the dial's right, or do we think that our range includes the answer? We keep doing that in our head over and over and over again until we get to a point where we can't choose between the dial. All right. In this case, the capacity is 90,000, stated on the website, and you do that for all these things. So if you take Hubbard's calibration tests, there are a ton of questions there that you have absolutely no possible idea of knowing. And you have to get used to the fact that when you face with something like that, you put very big ranges in place. And that's the point of risk measurement and measurement as a whole, is the reduction of uncertainty. So if you don't like your ranges you come up with, you have to come up with a test or a measurement that'll help you reduce them. It's really simple as that. Okay? So you can do this and you can start getting some pretty accurate ranges. All right, so here's a quantitative risk example. I live in Los Angeles. If a traffic incident occurs during my morning commute, I will be delayed. Probability, 1 out of 3 days, I see a wreck. Simple as that. The impact between 5 and 60 minutes. I'm saying 95% of wrecks are going to delay me by an hour or less, or 5 minutes or more, right? That's what I'm saying, in that range right there. Some will be much longer, some will be shorter, but 90% of them are going to end up right there. Monte Carlo is you take that probability of occurrence, and you take those ranges in a log normal distribution, and you start plotting the occurrence values and how many you generate. So this is a snapshot from Hubbard's spreadsheet. You put the probability of occurrence, your lower bound and upper bound, the number of trials you want to do, and you go through it. So trial 1, what you do is you take a random number from 0 to 1, 0 to 100, whatever you say. If it's less than your probability, then it occurred. Trial 1, it didn't happen. Okay. Trial 2, I got below 30, and my delay was 14 minutes. So on and so forth. You see a 50-minute there one, and you get all those. So the question I want to know is how many iterations are enough? Because Hubbard's spreadsheet's actually limited to like 10,000 because of the way he does it in the Excel spreadsheet. And I was like, is that enough? I don't know. So of course I wrote my Python code and I did a test. So you can see with 100 iterations, you can get a general idea of the shape. With 1,000 iterations, you get a better shape. And then between 10,000 to 1,000,000 iterations, there's not a lot of change in that curve, right? Those are those curves. I feel like I'm attached to a core, but I'm not. I got used to that. You see these curves here. This is the 10,000, and then the 100,000 and the 1,000,000 are right on top of each other. Now, this isn't a lot of computing power. I do this on this laptop, and that takes, I don't know, 20 seconds to run. So it doesn't take that long to get 1,000,000 iterations, right? And then when you have multiple risks, it takes a little bit longer. We get into the detailed risk decomposition stuff that I'm going to show you in a little bit. It does take a little bit longer because I'm running a lot of log normals. But the bottom line is you can run these on a laptop easily. You don't need big computing power. Now, also, this greatly the probability event greatly impacts how many runs you need to do. So if you're talking an event that has like 0.1% of a chance of running, you need to run 1,000,000 events or more in order to get a smooth curve. But it's obvious in the data. So when you print it out, you'll get the stair step stuff. You get these stair steps, and you'll know I need to run more rounds. As simple as that. And so you turn it up a little bit. But in general, between 100,000 is good enough to get you a good feel for where you're going. So it doesn't take that long. That's Monte Carlo simulation. Any questions on that first? There's only a few people here had studied it before. Okay. All right. It generates what's a loss exceedance curve. A loss exceedance curve demonstrates how much you can you can expect your impact to be. What you do is you take your min value and your max value. So min value is 1, max value is somewhere out here. This is a log trout, so it's somewhere like 250 or so. No, that's over 300, isn't it? And you do an equal number of intervals, and you calculate the number of events that equal the impact or greater. There's always or greater. So at the 1 here, so 1 minute or greater, 30% chance. And you keep going down the path, and you'll see where you get to. So we're saying I have a 30% chance any given day. This is my traffic one. 30% chance any given day of being a minute or late or worse, late for work. Let's say I'm not doing so good with my boss, right? I need to make sure I get there on time. I need to lower that to 5%. You can use the loss exceedance curve to find that out. So 5%, go over and down. You're talking you need to leave somewhere around 35 minutes early, 36 minutes early, in order to make sure that you are on time at work, all but 5% of the time. All right? That's how you use the loss exceedance curves. And this is what the risk generates every time. All right. Okay, now let's go over practicalities. That's kind of the theory, and then when you start trying to think about how you want to use it, you start running into some problems very quickly. The first one was curves are pretty, but I need to rank them, right? If I have curves like all over the place on there, and they all intersect each other, which one's my greatest risk? I don't know, but certainly my boss wants to. So you reduce the curve to a single number, and that can be done by calculating the area under the curve. This is exactly how the catastrophe insurance industry does this. When they have stuff like earthquakes and hurricanes, things that they don't really have, actual knowledge of what's going to happen, or good actuary tables, they draw these up and they calculate the area under the curve, and that's your premium. That's what they charge you in general, right? I'm simplifying. For all intents and purposes, the area under the curve is the mean of all of your data, all your results. I have a thing with it's five risks, and I checked the difference between the means and the area under the curve, and it was off by like 0.003%. So really, for all intents and purposes, just calculate the mean of your event. That's all you need to do. And besides, the area under the curve is approximated anyway, because you have to calculate with an approximation. So for my commute, on average, I'm going to be 7 minutes late, according to this math, right? Which is exactly why I ride a motorcycle every day, so I'm not 7 minutes late. But you have to watch out for the black swans. 241-minute max impact. So how do you want to rate your risks? Do you want to rate on the max impact? That has less than this is either 100,000 or 10,000 scenario run. The max impact was 241. That's a 1 in 10,000 or 1 in 100,000 chance of happening, right? Having lived in LA, when the Sepulveda Pass caught on fire, it happens. It took me 4 hours to get to work. In fact, I didn't even go to work that day. I turned around and went home. I'm like, no, the hell with you. I'm not doing it. So you have to watch out for that. So you need to choose how you want to rank your risks. It's probably not reasonable to use the max impact because it's such a small chance of occurring. But maybe that's what really concerns you. So there's that. And then I started having a lot of questions about Monte Carlo, about how do I use it. There's 3 independent variables that I'm using. I've got probability of occurrence, I have upper bound, and I have lower bound, right? Which ones affect my outcome the most? I got concerned about this. I mainly got concerned about it because it's really hard to pick a probability for your events, right? And we're going to go over that, how I did it, but it's very, very difficult to pick a probability. And so I was hoping that probability maybe wasn't that sensitive for Monte Carlo and I could get away with it. So I went over it, did models, probability, lower bound, and upper bound. And it turns out Monte Carlo is a precious snowflake. So for probability, you can see, I'm losing my audio, aren't I? Can you hear me? I'm good. Okay. Probability, you can see 30,000. If I modify the probability by 30,000%, the result modifies to 30,000%. So it's almost 1-to-1. So it's really important to not get that wrong or to take that error into account. You can see lower bound, almost no impact. No impact on the actual results that come out of the model. And upper bound has some impact, but probability, man, okay. And then it was even worse than I thought. These are order of magnitude bars. So like between 1 and 3%, you can see it, there's a change 200%, and the result changed 200%. It's almost 1-to-1. So not only is order of magnitude a problem, but within that order of magnitude, I can make this risk live or die as an important risk just by picking the probability incorrectly. And so that was a little interesting. And you can see it right here in the graph. Like I told you, the result, the average expected loss is the area under the curve. So when you change the probabilities, you get these big differences in the curves. And so of course the area underneath them is the big change. So that got me really concerned. I was like, okay, well, I'll handle that. I'm going to take care of this problem, this snowflake. I'm going to add error to my probability bars, right? So instead of a 1% probability, let's make it a half to 1.5%. That's a 50% error bar. So great, that should do it. Turns out it has almost no impact because over the course of 100,000 events, everything reduces to the mean probability. So I stated it at 1%. I moved it up and down. Honey Badger don't care. It's going to do the math, right? So I got to this point. I was like, okay. So I kept playing with it. Here's some bigger ones. Now I have a huge error bar, 5% with a plus or minus 4%. I mean, that's an enormous error bar. And then I put these other probabilities in there. We're going to talk about beta in a second. And then 5% fixed is just a 5% flat. And you can see the differences are not that big. So once again, because I said 5%, I am picking my results. And I did some more. Here's overlapping error bars, 4% and 5%. And you can clearly see when I pick 4% or 5%, like the math just goes right to it. The LACs don't lie. So that really got me really frustrated. I'm like, what am I going to do? And then I decided I am probably lost in the forest here. I'm not seeing the trees. I'm not seeing the forest because of the trees. And so I came to the conclusion that, yeah, this is a big deal. I need to be really careful about it. But the point of this is not to compare small variations of one risk to each other. It's to compare multiple risks across my company and identify the ones that have the most impact or least impact. If I get to the point where an order of magnitude change of my probability is how I'm switching my risks, I think that's actually a win. Now I know which ones I need to focus on. And I also need to say, hey, okay, yeah, they're flipping back and forth, but maybe the risks or the losses associated with that are not even fiscally relevant. Maybe they don't matter to my company's bottom line. Maybe they're just accepted risk. Maybe our insurance covers it. And then we also can get into qualitative differences at this point. I've now identified things I need to be interested in the quality of the loss. And what I mean by that, you're going to see a lot of this in a second, is how do I decompose my risk? Some losses are cost of opportunity. So your security engineers are there. They're working hard. We have a breach. Whatever they were doing before the breach, they are no longer doing. They are only doing the breach, right? That's a lost opportunity. But then there's actual costs. There's HIPAA fines. There's things like that. That actually cost the company money. Which one does the CEO care about more? That's up to your CEO, but that helps you figure it out. So I still consider it a win, even though we get to this really delicate position with probability. All right. Since probability is so important, I found myself considering, like, how do I think about probability? How do I cage my thoughts about it? So I started looking up, like, life events, statistically equivalent probabilities. So at the 150% chance of an event happening, I don't call that a risk. That's something you need to plan for. That's a cost of doing business. Because if you take that out, so say you do 6-month windows and you do aggregate risk across multiple 6-month windows, 50% probability, there's almost no chance you're not going to see it in the next year, all right? And you can check the math on that. So we're not going to talk about those, but let's talk about 50 to 10% probabilities. I call these my weather probabilities. And they're still really big, but they make a difference in your thought processes. For instance, since I ride a motorcycle most days, I check the weather every day in the winter, not in the summertime when it's 110 and there's no clouds. But in the wintertime, I check it. If the probability of rain goes over 20%, I won't ride. That's my risk level. If it's 10%, I will. So the point is there's a distinct feeling, intellectual difference between 20% risk and 10% risk, and you guys need to bring that in. And then you need to think, hey, someone says this cyber risk is a 15% chance of happening. Now you're talking like 50% chance of rain, like rain happens, right? So you basically be prepared for that risk to occur at that level. 10% chance of the next person you meet having a left hand, being left-handed, I mean. We all have left hands. 100% chance of that almost. Being left-handed. How many lefties do I have in here? We're well under 10%, but anyhow, that's a statistical life equivalent probability. So is this probability of a cyber thing happening more or less likely than a person with a left hand? A person being left-handed. All right, 3% chance that the next guy you meet does yoga regularly. Do I have any men yogis in here? There's 1, 2. Yeah, that's about right for this room. All right. So you need to think. Someone said that we're going to get breached on this website. Is that more or less likely than the next guy that I meet does yoga regularly? All right? That's a way to think about it. 1.5% chance of having twins. So I don't know about you, but twins are fairly likely. I mean, you know about them. But let me reset. I got to reset. I went too fast. Okay. I don't know anybody who has twins personally, but I know a lot of companies that have been breached. So if someone tells you that the chance of a breach is under 1.5%, you might want to be skeptical because there's so many companies that are breached. 1% chance of getting 6 winning hands in blackjack in a row. If we had all played blackjack last night, hopefully 1% of us had faced that. Did it happen to you? 6 hands? No. No. Oh, okay. My boyfriend's a blackjack dealer. Oh, okay, yeah. You know these odds. Yeah, all right. So 1% chance of that happening. 0.8% chance of being audited. I don't personally know anyone who's been audited by the IRS, but I know lots of companies have been breached. So if you start seeing numbers like this, you got to be skeptical. And finally, a 0.02% chance of getting a perfect score on the SAT. Life equivalent probabilities, just a way to think about things when you're faced with picking a probability for your events, or you look at data that gives you a number, which I'll show you how I do in a minute. There's that. Okay. So instead of just guessing and making up numbers, you can also use a thing called a beta distribution to come up with your probability distributions. And this is actually how I'm doing it. If you have a set of cases that are relevant to your task at hand, your risk at hand, you can come up with a probability distribution by counting the number of cases that count against you and the number of cases that don't. I do this on a date basis, and I'll show you how I do it. But basically it looks like this. The beta distribution like here says I have no information, none at all, about what's going to happen. So any chance between 0 and 100% chance is likely for this event. But then maybe I know 20 companies, and one of them got breached. So now I have 1 hit out of 20, and I get a little bump at the 5% mark, right? But when the beta distribution delivers a probability, it'll still pick along this line. You're just going to have a much higher chance than the 5% mark. And you can keep adding data. So as you meet more companies, you meet more people, more relevant cases, you can keep adding to it until you get a very high probability spike at the 5% mark, assuming that's the way it goes, right? So you can. This is a great way to keep your data fresh and your models fresh, and it's discussed in detail in Hubbard's book. All right, that's kind of the theory of all this stuff. Now I'll tell you how I did it after I drink my water. Okay, first I need to introduce you to my company. This is Motion Picture Industries. Anyone else work at a Taft-Hartley multi-employer plan here? I didn't think so. So what these are, consider them continuity benefit plans. So in the entertainment industry, there's all these people that work, and they go from Sony, they go to Paramount, they go to Disney. When they move, their contributions come to us, and they maintain their benefits as they move across jobs. It was put in place for craftsmen. There's many of these in LA. We handle, here, I'll show you. So we don't handle stars. That's like the Screen Actors Guild, basically. There's a Directors Guild, a Producers Guild. We handle everyone behind the camera. All right, so we're the largest, one of the largest Taft-Hartley multi-employers in the country. We get a lot of attention because of that. You can see what we have here. We have 48,000 participants, 18,000 retirees, but counting dependents, about 130,000 people that are subject to our healthcare plan, and we process, almost 2 million claims a year, healthcare claims. That's what we do. So we're a healthcare company, right? So that's the basis of my thought process. So what are my risks? Obviously, I'm a HIPAA shop, so I have to deal with that. So, I've been subject to audits and compliance checks, and consultants come and they give me lists of stuff. So I was trying to come up, and they call them risks. But I go through them, and they don't meet my definition of a risk. They are factors that contribute to risk. And I'll give you an example. So we got hit because someone saw someone moving PII to a cloud-based application, right? So it was authorized, it was fine. But that was something they saw. Hey, you're doing that. That's not a risk. One, because it happened, so that makes it an event. And two, it really just contributes to the magnitude of the loss I can expect. So work a thought experiment with me. Let's design a fake computer system that is fully air-gapped and only can transfer data through 3.5-inch disks, right? That's it. 1.44 megabytes of disk. There's probably 10 of those in the entire world, right? And probably 8 of them are at DEF CON right now. So that computer system versus my real computer system, which has internet connection to PII, unfortunately, my exposure is much higher. So it's not a risk. The PII, the fact that I use the cloud thing isn't a risk, but it contributes to the magnitude of my exposure. So I include it in my risk calculations, but it's not a risk on its own. So then I thought about, hey, let me look at all the applications, all the in-house applications we use, or the external applications we use. In fact, this is what Hubbard recommends as your best practice. But I have done full audits on all my applications, and I know which ones comply with HIPAA security rule, and I've already stated that audits don't result in risks, they result in factors that contribute to risks. That includes my own data, my own audits. So, and they all basically touch the same data on the back end anyway. So I decided that it wasn't doing an application basis that mattered. Instead, I decided to go with the CIA triad against my data itself, the data pools. And this is the exact one I'm going to model for you right now. So I said, in the next 6 months, you got to pick your time band. Risks are time banded. And I picked 6 months. You could pick a year. You could pick a day. Whatever you want. Just make sure your numbers work. There's an X% chance of medical claims data confidentiality breach of 500 records or more. 500 records is the trigger point for Health and Human Services. You go over 500 records, that's when the pain comes. So that's when I wanted to activate most of my cost centers. So that's why I picked 500 records or more. And the impact of that breach will be Y dollars. All right. So that's a nice statement of a risk, but now I got to get down to business. How do I calculate these risks? Okay, starting with the Y, the risk decomposition, because the costs are easier than probability, so let's just start with that one. Basically, I started with my cost centers. Watching the security process that I run, I was like, okay, I know when something happens, my engineers do this, and it takes them this long. And then I started thinking about, okay, if I had a big loss of data, probably multiple business units across my company would probably get involved in this. So I wanted to estimate that. So first, I did that. I broke it down into these cost centers based off of the actual department. And I estimate the lower bound and upper bound in hours of time I think it'll take to handle the risk, and then the lower bound and upper bound of cost per hour. All right? This is just how I went about doing it. The costs I use, they're rough. They don't match our salaries. I can't. HR would kill me if I put our real salaries on here, so I'm not doing that. and I just estimate the hours. Basically saying for security, I'm saying, hey, a small breach, small problem, my engineers will fix it in about 5 hours. A big one, 2 weeks. I can't see a full-time for anything longer than 4 weeks of full-on-time fixing a breach, in my opinion. It might be wrong, but that's what I picked. And then the salaries, I know how many people are in those particular divisions, and so I can cap the salary cost per hour. And I did that for every department in my company. And then I moved on to what I call my real costs. These are things that we'd have to end up doing, right? So if our code's shown bad, we're going to recode it, and we tend to use contractors for that. So that's going to cost us real money. We have an incident response retainer that I'll have to burn. Our legal consultants are ridiculously expensive, so I got to account for them and their arm retainer. Well, and buying a new tech control, right? I mean, everyone who's ever been through a breach knows you end up buying a new tech control. So we put that in there. So I call these my real cost centers. And so I kind of went through this, and I decided, okay, this is how I'm breaking down my risks and my costs. Each one of these ends up being a log normal distribution. That's why I use upper bounds and lower bounds and a cap, and it does the math. And I decided, hey, I need to compare this to people who have really looked at the cost of breaches. So, Pony, Sands, lots of people have done this. And I discovered that the cost centers I picked are actually really close to the cost centers that they bring up in their reports. And so although the costs are unique to company, I don't think the cost centers are that unique. And is anyone else here subject to technology business management from the CIO? Anybody? Nobody? Really? Okay. I'm not going to talk about that, but they have defined cost centers in that project as well, and they match up to the Ponyman cost centers. The point is, picking the costs for an impact of an event that affects your IT department or country doesn't need to be black magic. It doesn't. It's kind of defined for you. You just need to dig in and assign your numbers that you think make sense for your company, so that you can get to a good risk decomposition that way. And Hubbard goes through all this in his book as well about how decomposing the risks. And I don't have to do this, right? I could just say, hey, I think it's 10K to 5 million. Claims breach of 500 records or more, 10K to 5 million. I can just make that assessment, but I don't know if I have a real basis for that assessment. So I wanted to break it down. And I used the log normal distributions for everything except for HIPAA fine data. This is a statement for what a HIPAA fine can be, right? It's pretty big, 150K per year, max penalty of 1.5. Okay, but you can find HIPAA fines that exceed 5 million. You can find HIPAA fines that are a lot higher. So so what's this max penalty thing? I was like, you know what? Instead of guessing, I'm going to try and model it on real data. So I'm looking for real data. The Health and Human Services website has lots of information on current investigations, but almost no information on charged fines. But this website here does. This compliancy group, they have about 2 years of data. There's 26 samples in there. I was like, all right, I'm taking this as my model. I put it together and I was like, okay, I'm going to make that as my, I'm going to call it a standard distribution, like the bell curve. But the numbers didn't make sense. The mean and the standard deviation didn't work, so I plotted the data, and that is not a standard distribution. It just isn't, all right? So I was like, okay, now what do I do? I might be able to guess what that distribution is. I might be able to make something up. But I did some Googling, and I ended up on this site here, this Stack Overflow, and this guy, his name may or may not be Timothy Davenport, it's hard to know. He wrote this code that'll take your data and run every distribution in SciPy against it and come up with the one that fits best, and then give you the parameters so you can use that distribution in your code. It was amazing. I loved it. I've generalized it a little bit, and I made it so you can use other things besides what he did, and it's called model fit.py. It's in my it's in my repo. You can use it, and it'll generate the fit for you. This is what it did for the HIPAA data. I don't know what I'm looking at. I'm like, okay, that's like basically a blank graph. Thank you. But it gave me those numbers up top, the settings that make the power law work, and it says, hey, it's a power law data system. That's interesting. It's a little dangerous because power law can get really, really big every now and then. But I was like, okay, well, here's what I'll do. I will take 26 samples out of this new random distribution, and I'll plot it next to my actual data, and we'll see what it looks like. So here's the original data. That's what it looks like when you plot it. Here's my model. I'm like, all right, okay. I mean, is it Gordon? I get his name wrong. George Box. Someone says, sorry, last name's Box. I'm pretty sure. Says that all models are wrong, but some are useful. I think that's a useful model. So I use this to model my HIPAA fines for all my events. Now, all right. So I got my costs. Now let's talk probability. So we talked about this already, that I had to be careful about this. Like I said, I can make my my risk, live or die, based off of this number that I pick for this event right here. And that frightens me. That's a lot of pressure to get right. I started thinking about it, and I was like, okay, the absolute value of my risk probabilities probably matters less than the consistency in the way I pick them. If I'm consistent across all my risks, then my risks can be compared against each other. But if I'm just yanking stuff out of the air every time, then I'm probably not going to be consistent, and I can't compare my risks equally. So I decided to go with beta distribution. Basically, I'm saying you pick a time window. I said 6 months. You have your data. You associate with dates. You can see these red marks here. This is sample fake data. You can say, okay, I had a breach in January, a breach in March, and a breach in November. And then I move that six month window. Okay, this is a hit. This is a miss, or this is a hit because it got that one in March in there. This is also a hit, so I'm up to 3 hits. And now I get to April, and I have a window where I didn't have a breach. So now I've got 3 hits and 1 miss. Same here with May. And eventually, you do this through all your data. I did it through my breach data, and I had 1 hit and 20 misses. I use that in my beta distribution as I show right there. That's the way I pick my probability based off of MPI's actual history. Now, we actually haven't had a breach of that magnitude, but when you start from a 0 knowledge baseline, like I said, that means you start with 1 hit and 1 miss, and then you have to add your new data on top of it. So you always have 1 hit. It's just the kind of way it works. So I wrote a piece of code for that. You can give it the time window you want. You can give it the sliding time window. You give it your dates of events that meet your criteria, and it'll calculate your beta parameters for you. It's right there in my repo. And it's not exactly perfect, I'll be honest. There's some weird edge cases that it doesn't handle right, but it's close. Okay, so I got to the point now where I'm ready to code. So I coded it up. First, I do my cost of opportunities. These are my manpower costs. Then I do these are my real costs. You can see what I did there. I put it all in a simple model, and then I ran it. And all this code is available. I put the whole claims risk thing in there. I think it's claimsrisk.py. It's in the repo, so you can see exactly how I use my own models and how you incorporate them. And this is the result. Okay, any questions? All right, no. All right, so basically I'm saying I have a 5% chance of a $10,000 loss or more in the next 6 months. Okay, and then you can get down there at like the $1 million mark. I'm at like a 3% chance. At the 1% chance, I get down to some pretty big numbers, especially for my company, like 2.5 million. Now, is this good or bad? That's up for the CEO to decide, and you have to go with them, and have a conversation about risk appetite. You go, hey, CEO, 2% chance of a $3 million loss. You happy with that or not? And they have to decide. That's their job. They have to decide whether the business can absorb that kind of loss or not. And you can plot their results on top of this and see where you need to impose mitigations on top of that. I haven't gotten to that point yet. The CIO is happy with this. I haven't gone to the CEO yet. And one thing I didn't cover, on the probability. So the beta distribution is giving me my baseline probability. But what about new factors? What if I say, hey, I'm exposing a new public API in the next 6 months? I'm bringing a new code contractor with an uncertain history. All these things affect the probability of my breach occurrence. And there's a whole section in Hubbard's book about doing a mathematically consistent way using Bayes' theories to include that data in your math. I didn't get there yet, but I am heading in that direction. So I encourage you to read that section. He has a spreadsheet you can download to incorporate different pieces of information. You'll notice it doesn't look like this. This is what my original risks I showed you look like, and they have that nice little fancy tail. That's because I capped all of my losses. I chose to do that. If I turn those caps off, I will get the S tail, and you'll get the big black swan. You need to decide whether you want to do that or not. But bottom line, this is what we ended up with. And it's kind of the setup we're going to move forward with. So where am I going from here? And I'm short on time, but I'm not short on time. I'm moving too quick. For me, I need to do the integrity and availability of the same data. And this requires a fairly in-depth interview with the business units. Like, hey, if the integrity of your data is messed up, what is the actual impact of the business? The availability is messed up. What's the impact? Like, I've discovered that if my claims data is not available for 2 weeks, then we end up paying 100% of claims, not 90%. That's a substantial monetary impact. So I have to look into that a little bit more and model it. So I need to do that for my claims data. I need to get into the considering other factors on the probability. That's important. I need to model my other data stores. I've also got eligibility data. I have retirement data. I have lots of other information I need to look through. And then the big thing to do, I need to carry my manpower versus actual costs through. Like if I showed you on this slide here, I don't know the makeup of this. When I talked about the qualitative review of is this mostly real cost or is it mostly cost of opportunity? I don't know because my model doesn't carry that through. I can't tell. So I need to kind of add some hooks in there so I can see that data. I have more ranks to do, or more risks to do, and then I talk about mitigating them. And I need to formalize the process. If I'm going to get this through HIPAA compliance review, this has to be formalized and documented and all the fantastic things that make life so fun. So I got to do that. For you guys, I recommend going to get Hubbard's book. It's on Amazon. Go get my code. There's the repo right there. I'll leave it up there for a second. And then think about how you want to decompose your risks, how you want to calibrate your team, and then do the models and simulations. I think it's really worthwhile. Yeah, I think it's really worthwhile. I like this method way more than the heat maps, the standard NIST ways of doing this risk. I can add new data. I can compare new risks. I can do everything I need to do to make this work for me and my company. Stuff I was never able to do with your basic heat map risk work. And that's kind of where I'm at. So I'm a little early, but I'm open for questions. Yes, we got one. Oh, sorry, we gotta wait for the mic.
I'm so sorry I got here late, but did you cover reputational risk or attempting to quantify the softer costs or
you can if you think that's relevant to your company. So Hubbard has a whole section on that.
Okay, is there any company that's not relevant for?
He will show you that the math shows that reputation isn't affecting bottom line on companies in the long term.
I've heard that like beyond 6 months, like even stock prices recover it, and so
like even in the book he talks about target, the target loss, and the dip in target was indistinguishable from stock noise within months.
Thank you.
So there's that. We have one up here.
I had a question on residual risk and being able to track after the mitigation of whatever action has taken place to reduce that, and how you're tracking a risk past the initial point of identification.
Right. So you're saying you identify a risk, we get the CEO's curve, and we don't, and we're too high, so we need to reduce some risk on that.
You have a series of risks that you put together that help identify things. Again, you were kind of mentioning this whole idea that, the probability of this one thing, you can kind of get into the minutia of how do I rate that, but it's really valuable on the metascale of all these risks put together. Mm-hmm. However, after you go through that and maybe you change that environment's situation, that attack surface, and now you reduce a specific risk within that, how are you tracking the residual risk in terms of kind of applying this? So risk is not it's a point in time.
Yes.
And so kind of how do you continue to model that through?
So the only thing you can do, so if you're going to do a mitigation, it needs to either reduce the impact or the probability of the event by definition, right? And so you have to make an assessment. If you're going to buy a new Blinky box, you're saying my Blinky box is going to reduce my risk because I'm going to cut out 17 more attack vectors, so probability goes down. Something I haven't gone into yet that I'm planning on is I'm also a MITRE attack matrix kind of guy. So I want to show, hey, currently I'm not detecting these things, but now if I buy this Blinky box, I'm going to have these more things I'm going to be able to see and stop. And so I'm planning on attempting to use a beta distribution to show how that reduces the percentage of probability. But I'm not there yet. So, but bottom line is we lots of times get offered solutions and services that don't reduce probability or impact, and they're really quite worthless from a risk perspective. And so you have to take that into account and make an assessment. You need to estimate what you think the risk reduction will be. If you're not convinced there's a risk reduction, then don't buy it. Yes.
So from your modeling, it looked like the probability was one of the biggest effectors of all of this calculation. Is there any sort of movement to standardize the probabilities of incidents that across industries? I
can basically say no, right? I mean, nobody wants to share their data, right? You have to base it off of your particular industry. Like I can look at healthcare companies and say, how all these companies got breached. Are they relevant to me? Do I focus on Taft-Hartley multi-employers? Do I focus on the entertainment industry Taft-Hartley multi-employers? There's only like 6 of them. That's not going to give me very good data. And So the answer is kind of no, right? You kind of have to grade the data how you want, and even though there's a lot of, like, there's ISACs and there's Cyberhood Watch with the FBI, still the sharing of data on actual breach and how things are breached is really, really sparse. So that would be super useful. And people talk about, hey, the cyber insurers have good actuarial data, but I don't think that's been proven to be true either. So there's a lot to think about on that perspective from an industry perspective. Yes?
So there's a lot of talk about velocity associated with risk assessment. How fast is you're going to realize that probability? Is that factored into your model at all, or talked about in the book?
No, I didn't. I haven't gone there with that. So I think you have to talk velocity if you don't talk about time windows. So you're like, you're like, hey, I'm setting this to my 6-month time window. And you're like, this is my risk for that window. If the factors change, then the risk changes. But he doesn't discuss velocity in his book. So, any other questions? Yep. Oh God. Oh God.
So you modeled a lot of this stuff, at least in your examples on your personal life. How much earlier do you leave for work now?
Because I ride a motorcycle, I don't. That's the great thing about LA traffic is I do the white line exploiting through the LA firewalls every day. So it basically takes me 35 minutes no matter what's going wrong, except for complete closure of the freeway. But anyone else? All right, thank you guys very much.